as we have noticed, the principal task of the control unit is to generate a sequence of control signals to effect data transfer. We have seen the design of a hardwired control unit. Let us today examine the design of an alternate way of realizing a control unit. First, let us examine the instruction execution a little bit critically and analytically. Okay. Let us come to that instruction fetch. Okay. As we have seen already, that in the case of an instruction fetch, first the content of program counter should come to memory address register. Then the content of the memory at memory address register location should come to the memory buffer register. Program counter should be incremented by 1, and the content of memory buffer register should come to the instruction register. Okay. Now, if we look at this, you can see that this more or less looks like a program, okay, written in fact in some symbolic language. For example, if we put an equal to, say MAR equal to PC means that content of PC should go to the location MAR. Okay, therefore, we can see that each of these instructions are essentially is a machine instruction kind of thing. Okay, and we call this micro instruction. The corresponding code is say C0 to C12. If we take the machine, okay, we see that these are the control points. Just to have a C0, where is the C0? The C0 to C12, C0 to C12. Oh, this will be C12. I think that it was missed. Okay, therefore, you please take correction. That C0 to C12 are the different control points that are to be gated as per this code. Okay. Now, this we call a control word. This is the corresponding action that has to be taken. And if we look at that control word, we can see that this is as if it's a machine language instruction, right? So 0, 0, 0, 1, and so on. Now, for our convenience of referring, let us encode it in an hexadecimal form. Okay, then in that case, it is 8. From here to here, this is 8. This also is 8. This is 0, and this is 0 in hexadecimal. Therefore, this control word, which means that PC goes to MAR, okay, content of PC goes to as content of MAR. The corresponding control word is this, and corresponding hexadecimal for our ease of reference, hexadecimal form is 0088, right? Now, this is a control word. Each one of them we call a micro operation. For example, this is a micro operation, this is a micro operation, this is a micro instruction. Now, if we now arrange these micro instructions one after the other, the way that the micro instruction should be executed, in that case, this forms what we call a micro program. Okay. Now, let's see if we take this, that fetch, that micro program in the symbolic notation is this. The control word for the micro program is 0088 in hexadecimal, all zeros here, 0001 and 0202. These are the control words in hexadecimal for these micro instructions corresponding. Okay. See, these 4 I have taken that, so as memory access is concerned, that all the control signals will be 0, and therefore I have taken it to be all zeros here. Okay. Now, you see now that these control words, which we can take to be that machine level, okay, instructions, this control word can be kept in a memory, and if we can execute these control words, execute this program in memory, the machine language version of it, in that case, basically we can think of that as if that these signals will be generated one after the other. For example, if the control word is 0088 and this is memory, and if we fetch this content of this memory location, then this will be the output that will emerge from that memory that has been shown in the red line. And this, if we now send to the different control signals, for example, these two control gates, this to C0, this to C1, then as we read the content of this memory location, this content, okay, the output of the memory location, this memory location can be set directly to the different control gates, which will affect the control that is desired to have program counter going to memory address register. So after this is over, we can keep, so to say, a program counter kind of thing, okay. Then the program counter can be incremented to the next location, and this location can be read, and the next micro word can be executed, which means that next micro instruction can be executed. Now, this way, if we arrange, say, the program for the fetch keep the program for the fetch in a memory we call the control memory, in different memory locations, say, starting from 00 to 1, 2, and 3, say memory location 0 contains this, memory location 1 contains this, and so on. And if these instructions are executed one after the other, starting from the memory location, control memory location 0, then the control words will be fetched one after the other, and the effect of this control word being fetched one after the other is similar to that executing this micro instruction one after the other, which means that opening gates in time sequences as is desired to fetch an instruction from the memory and put into the instruction register. Such a program is called a micro program. The memory is called that microcontrol memory, okay, and this all the operations that it needed for the controls can therefore be kept in a memory one after the other, in the control memory one after the other, and that micro programs for corresponding to each of the different machine cycles that we have talked of already, in that case, will constitute the total control unit. Okay. For example, I have said that this is for the fetch. Register indirect addressing, say, where the content of the memory location to be addressed is contained in a register, right? In that case, you see that micro program transfer to be content of R should go to memory address register. That is, say the address is 0025 in my control memory, and the content of that memory location 0025 should be 0480 as per the necessity of the control word. Okay. Similarly, the control word for this is all zeros, and say this is in the memory location 26. Control word for MBR going to some, say, temporary register T, okay, is this, right? Naturally, this particular control word will change depending upon where the content of memory buffer registers is to be sent, and therefore this may need the consultation of the instruction register field. Okay. Now, let us take another example. Say this situation, the microprogram for the addressing mode direct, indirect. Okay. If it is direct, let us see what happens. That program counter should go to MAR because, so for example, in the case of a direct addressing, the situation is that, say for example, I say move say M to say some register R. In that case, the instruction in at machine level will be the first word will contain the instruction say move. This is say destination, and this M mode will say that this is a direct addressing, okay, and the content of say the location is say lock. In that case, the address of the location lock will be the next word, okay. So when this particular instruction has been fetched, the program counter is now pointing to here, and to get that address content of that memory location, the program counter content, which is the address of lock, should be sent to memory address register. See the address in the control memory where this micro instruction is kept, whose corresponding control word is 0088, okay, is location 50. Then say the location 51 will contain all zeros corresponding to this micro instruction. Location 52 will contain the program counter is incremented. Okay. Now, after the program counter is incremented, in the case of that direct addressing, then the content is already, that means operand is already in that memory buffer register. Therefore, memory buffer registers can be sent directly to the designated register R. Therefore, after program counter is incremented, we should execute this instruction straight. Okay, that means after program counter is incremented at the location 52 by this control word, okay, we should come to the location 0056. In this micro program, we have indicated that if this jump condition is 1, in that after execution of this instruction, the control should come to 0056, where the memory buffer registers will come to the content of memory buffer registers will come to the designated destination register. But if it is indirect addressing, then instead of jumping from this memory location 52, control memory location 52 to control memory location 56, the content of memory buffer register should go to memory address register once more. In that case, what we have is basically an indirect addressing, right? And therefore, the situation say is this, that means we go to the content of memory location point to 2 by the content of the location address. Okay, basically the situation is somewhat like this, as I said, that's indirect addressing. Say this is our lock, and this is in fact is our operand. This operand's content is pointed to from this memory location, okay, and this contains here, which essentially means, and this is generally indicated, say in our assembly language, we'll say that this is as if indicated by means of say some symbol like that. This means that it is indirect addressing, okay, and in my machine the mode will be represented this way by some, coded form. Now, if that be the situation, then in the case of an indirect addressing, the after program counter is incremented here, content of memory buffer register, which now contains the content of location lock, should come to memory address registers once more, and then, which means now the memory address register is pointing to this location, right? And content of that memory address memory at that location, that means pointed to by memory address register, should come to the memory buffer register. Program counter should be incremented once more here, so that it now points to the next instruction, that is next to this move instruction, that is here, and memory buffer register content of memory buffer register should go to the registrar. That is my indirect addressing. Okay. Now let us see the situation that in the case of a direct addressing, we go to this micro instruction, then this micro instruction, this micro instruction, and if it is a direct addressing, we come to 56 and the content of memory buffer register is sent to the register here. In the case of an indirect addressing, instead of making a jump here, we execute these control words immediately after it. Okay, that means we go through this micro instruction, memory buffer registers go to memory address register, then this micro instruction, then the program counter is incremented on, and MBR goes to, content of MBR goes to the register. Now, as I said earlier, the sum of these micro instructions can be clubbed together, but that's a minimization procedures of these micro instructions. Okay, and if one can very critically examine these micro instructions and try to see what control words can be merged with what control words and minimize this total micro program for a particular addressing mode, right? Now, what we intend to show you here is that in my total micro control memory, okay, micro program memory, that in different locations, what we'll keep is that it will keep the CPU control word one after the other as the micro instruction demands. We also, in some field, another fields, will keep the address of the next instruction that will be that one the microcontrol will jump to for execution of a execution of a microprogram as the logic demands. Okay. Therefore, each microcontrol word therefore consists of three fields. One is that what is the control word which controls the gates, that means control signals that goes to the control gates. Another field is a jump condition. It says that on what condition that next instruction we jump to, at what location it remains. That means that, for example, here, that if the jump condition is for direct, then we go to memory location 0056. Otherwise, we automatically go to the next memory location. Therefore, jump conditions tells that when to take a jump, and the address fields, okay, if the jump condition is true, then the address field tells me that what micro instruction we should jump to have the next micro control word for execution. Okay. Now, let's see, therefore, what will be the general nature of a micro instruction format. The general nature of a micro instruction format will be that here it will be that internal CPU control signals, okay, from here to here the control signals, right? So, for example, the CPU control signals. Now, the control unit is not supposed to control only the gates within the CPU. It is supposed to send control signals to the external bus also, like say memory read, memory write, etc. Okay, the write done or data ready, that kind of signals are to be taken care of, right? Therefore, one field will control the internal CPU control signals, another field will control the external bus control signals. There will be a jump condition depending upon the condition that which next instruction, what's the address of the next micro instruction that was to be taken, and in that case it gives us what is the address of the next micro instruction, where to jump to if the jump condition is satisfied. This is if this be the situation, that means if we take that for every control gates like C0, C1, C2, there is exactly one bit, which 0 means that it is closed, 1 means it is open. For every control gate, if there is a 1 bit, then it is called a horizontal micro instruction. Okay, and if we write a program consisting of the horizontal micro instructions, then we call it a horizontal microprogram. Each horizontal micro instruction will have the format like this. Right. Now, with this, let us see what should be the structure of a control unit, which we call a microprogrammed control unit. In contrast with the control unit that we had done earlier, which we call a hardwired control unit, where the entire control signals were generated by means of a hardware circuit, which is interconnections of the gates, flip-flops, etc. Here, the control signals are read from what we call the control memory. Now, let us see what are the components of this control memory. Naturally, that instruction should come from the memory and will be channeled to instruction register here, which will be decoded, and the decoded output should come to what we call a control address register. Previously, in our general program, in the situation of a general program, we called it program counter. Here, the program, instead of program counter, it is called the control address register. Okay, and with the program counter, that in the terms of the memory, we call it a memory address register. It is called the control address register here. Okay, this is the control memory. The width of the control memory will depend upon that how many bits are needed here. Okay, generally it varies from say around 30-40 to more than 100, say 120 or so, depending upon the hardware. Okay, depending upon the machine, right? Now, naturally, the content of the control memory at that control address register is fetched, okay, is read and comes to what we call that control buffer register instead of memory buffer register, right? That memory buffer register is decoded. We keep this decoder. The purpose we will say after some time that it now generates the control signals directly. One set go to the CPU and one set go to the system bus, right? For example, say one set should go to the CPU control signals, and another set of control signals goes to the external bus, right? Now, let us see that what's more needed. Naturally, we'll have to have a sequencing logic that will sequence the execution of this microprogram. Okay, that means as it goes through instruction after the instruction, this input to the sequencing logic should be from the decoder, because as I said that instead of the next instruction, it may have to jump to some other memory location to get the next logically sequential address, okay, of the microinstruction. Therefore, one input will come from the decoder to the sequencing logic. The other input should come from external also. External, that means, for example, some interrupt signal comes, right? In that case, the sequencing logic should go to that interrupt handler, which will be in other part of the memory within the control memory. Now, the internal signals like say condition codes like overflow, carry, sign, etc., those should be inputted also, and that should influence the flow of control within the microprogram, and that sequencing logic will decide what should be the content of the control address register from where the next micro instruction are to be fetched. Okay. This, therefore, you see that is the general structure of a microprogram control unit. The sequencing logic also gives a signal, right, that to read the content of a control memory, and an input to the sequencing logic will naturally be the clock. Okay, all the operations will be synchronized with the clock signal. Right. Now, this is a model you can see that can be, I should say, that very methodically designed from these microprograms as we need, then write the control code and then choose the error space and then load the control memory with these control words to have a control unit like this. Okay. Now, this model was first proposed by M.V. Wilkes in early 1950s, but though it was a very methodical way of design, a very simple way of designing a control unit, it was not very popular because you can see that if this control unit has to work satisfactorily, then the control memory has to be very fast, because the total control will depend upon how fast the memory contents from this control unit can be fetched. Okay, since till mid 1960s, the contemporary technology could not give very fast control memory. Therefore, though the idea was very much promising, the implementation was not there till IBM announced IBM 360, a very successful machine in mid 60s. Since then, the microprogram control unit turned out to be very popular, and in many machines, okay, including machines, I mean very modern machines of today's, use microprogram control memory. Right. Now let us see, we see that we have seen simple that microprograms for that different addressing modes, microprogram for fetch. Let us see that what will be the structure of the total microprogram. Okay, actually in that microprogram I have written, so to say, in algorithmic form, that say from fetch microprogram, that ultimately that machine instructions should come into instruction register through this microprogram. Then after that, it should jump to the source, okay, SRC point in the micro program if needed. That means if source cycle is needed. If not, go to DST if needed. That means if the destination cycle is needed. Go to execute if needed. That means go to execute cycle if needed. If none of them are needed, go back to fetch to fetch the next instruction. Now, in the case of either source or destination, naturally that address, depending upon the addressing mode, the operand has to be fetched, right? Therefore, we'll have to go to the microprograms or micro subprograms corresponding to different addressing modes. Now, one important thing I should say here, that say for example here go to or jump, all are unconditional jumps, etc., that we have talked of. The conditional jumps are also there, as we have already indicated in the case of direct indirect addressing mode. We can also use one level of subroutine jump. Generally, in the micro instructions or microprograms, not more than one level of subroutine jumps are allowed. Okay, because the subroutine jumps, as we have seen in general programming, that takes time, and we cannot afford to lose much time in the case of a microprograms, because the more you lose time, the slower will be the machine. That is why, though I have seen for my logical structuring point of view that it goes to source, then from the addressing modes, what is tried to be done, these transfers of controls are tried to be optimized as far as practicable, so that unnecessary time is not wasted from moving from one micro instruction to the other micro instruction. But just to have a logical structure in that how it can be structured, okay, A possible way of structuring, I have shown it this way. Similarly, execute will tell jump to the operation point of that microcode where the different op codes will be executed. That means add, subtract, multiply, divide, logical, and etc. Right? For example, that microprograms can be like this. Here, that addressing modes can be register addressing mode, direct, indirect addressing mode. If all addressing modes will be there, control will be transferred to the corresponding sub-program, okay, sub-microprogram to fetch the operands. Okay, it may come either from the source cycle or from the destination cycle. Similarly, when you come to that execute for adding, subtracting, multiplying, ANDing, comparing, okay, for executing JMS instruction, jump to subrouting instruction, which is given call instruction, so to say. Separate microcodes will be there, separate subprograms will be there, okay, which will be executed. And after execution of each instruction, each subprogram, the control should come back to the fetch once more. Okay. Therefore, the entire microprogram can be arranged in small subprogram, in terms of small subprograms within the microcontrol memory. Okay. Now, let us examine a little bit more detail that what can be the structure of a microcontroller realized in terms of microprograms. One thing I've forgotten to mention here is this, though I have shown that, for example, source, destination, execute, etc., naturally what exactly will be the cycles that will be decided by that how many operands an instruction has. Okay. As I've said earlier, there's an overall discussion. I've assumed 2 address machine. Naturally, it has to be cut to fit 1 address or 3 address or any other addressing modes. Okay. Now let's come back. This is the control unit shown in somewhat more detail. Here you see that I am basically trying to show that what can be the branch control logic here. You see here that here is that control address register. From there it comes to the decoder. Okay, that means control address register, which particular address it goes, the decoder decides. Okay, the control address register content is decoded, and that particular content of that memory is fetched. That comes into what we say that control buffer register. One portion can be that address that comes into this multiplexer. Control address registers can be incremented, okay, here, and can come to this multiplexer. Instruction registers content also comes as an input of the multiplexer, and that interrupt address, in the case of the control unit has to handle that interrupt address also comes into that multiplexer. Okay. Now, depending upon this branch logic, where the flags and the external signals, when control condition flags like that carry overflow, etc., external signals including interrupt, okay, then the data ready, write done, all these comes into this branch logic. Input from that control buffer register, that portion which controls that branching, that input also comes over to here, and that decides that out of these 4 possible ways, that means this address one that comes from the control memory, that decides by the instruction register itself, that comes from that interrupt handler address, I should say, the program that handles interrupt, that input, and the control address registers incremented that input. Any of this is now channeled through this multiplexer into the control address register. The job of this multiplexer is that depending upon this branch logic, it decides out of these 4 possible places where the control should be moved to, which one is gated into the control address register, in that case, that particular memory location's content will be taken, and which means the control is moved to the control memory location that control address register points to, right? Therefore, this tells me or gives, what should I say, that a picture of the branch control logic, right? Now, in many microprogram control unit, instead of one address being kept over to here, and the control address registers incremented and comes into that multiplexer, instead of that picture, the picture sometimes is this, okay? That instead of that one address, two addresses comes from the control memory, that address 1 and address 2, and depending upon the branch logic, that means the branch condition that is kept in the control word and the condition that actually exists here, either address 1 or address 2 is put into the control address register, okay? Therefore, the control flow is decided by this way, that either it goes to address 1 if the condition is satisfied, say, or to address 2 if the condition is not satisfied. Naturally, that multiplexer, the other two inputs will be from the instruction register and from interrupt address, okay, to handle interrupt, okay. And the one of these four inputs, that means address 1, address 2, instruction register, or the interrupt address, is gated into the control address register, which decides what will be the next instruction that will be executed, right? Therefore, either situation is that either you have two addresses or you have the control address register incremented and comes to the multiplexer. This is the two way that we can execute the branch control logic. Now, one thing that we should see here, that as I said, that if we go for horizontal microprogramming, in that case, that you see the total control word turns out to be too huge, too big, say sometimes more than 100, 120. Therefore, we should see that whether we can do something to reduce the size of the control word, right? Few observations we can make, and the observations are this, that say a register cannot be simultaneously be source and destination, okay? More than one source cannot be gated into the same destination. Right? But only one code can be the input to an arithmetic and logic unit, and the control signal sent to the external control bus should be consistent. By that I mean that both memory read and memory write cannot be simultaneously true. Therefore, if we make such observations, we'll find that many control points, okay, cannot be simultaneously gated, right? Either, that means, for example, there can be two control points, say A, B. A and B cannot simultaneously exist. Either if A exists, then B cannot exist simultaneously, or B cannot be active simultaneously, or vice versa. Now, if that be the situation, say I have four such control units, control points A, B, C, D, okay, which are mutually exclusive, then to code them, only 2 bits are sufficient. What we'll be needing is once more a, say, decoder, right? Where we put, say, two control points, one says C0 and says C1. The output of the decoder with the 4 lines, okay, say A, B, C, D, right? If it is 0, 0, then A is high, others are low. If it is 0, 1, then B is high, others are low, and so on. Therefore, we can decode sorry, we can encode these 4 control points A, B, C, D by means of 2 bits C0 and C1. Okay. Now, if we encode it this way, which are mutually exclusive control points, right, then we can reduce the number of fields. Okay. And say this is an example of an encoded microinstruction. All right. Here you see that the entire control word has been divided into fields, say field 1, field 2, field 3, and say field k. All the control points that are here in field 1, that is encoded by field 1, are mutually exclusive. So is all the control points, okay, that comes from field 2. But any control points in field 1 can be simultaneously operated by any control point in field 2. Okay, therefore, they can mutually be at the same time, can be executed at the same time, but any control point here are to be executed in mutually exclusive time. Okay. This way, if we encode that entire control word, you can very easily see that the control word size turns out to be much smaller. For example, say if it is 4 control points which are mutually exclusive, 2 bits are needed. Similarly, for 8 control points which are mutually exclusive, we need only 3 bits. Like for example, if there are k control points which are mutually exclusive, then we can have log 2 of k bits in the field ceiling of it, right? That many bits is needed to have k control points energized, right? Now with this, okay, we can reduce the number of fields in that control word, and such a situation we call a vertical micro instruction. In contrast to, as I said earlier, the horizontal micro instruction, where we have a bit for each control point in the control word. Now the terms that horizontal or vertical are, so to say, it's not very precise terms, okay, but they are, so to say, vocabularies, right? That horizontal micro instructions, vertical micro instructions, sometimes it's called, say, diagonal micro instructions, in the sense that some is coded and some portion is not coded, okay, but they are not very precise terms as such, right? Now, with this, you see that we can have a very systematic way of designing a control unit through microprograms, right? By using micro instructions and microcontrol memory and sequencing through the micro instructions in the microcontrol memory. The advantage are several, so to say. Firstly, that it is simpler to implement and is flexible. By flexible, I mean, so for example, in the case of a hardware control unit, once you have decided about that instruction set, if you want to add one instruction, right, you immediately see that we'll have to go through a very large scale change of the control unit design, okay? But in here, what we'll have to do is that we'll have to add a sub-program within your complete, microprogram, okay? And the total control memory has to be loaded once more accordingly, right? Another advantage is that it is cheaper and less error prone, because you see that it's a program and we can debug it easily also, right? Third important point is that user programmability is possible. By that I mean, if we know in a system what are the control points, right, and the microprogram, if it is a writable microprogram, okay, or for example random access microprogram, program memory, in that case we can write our own microprogram, load into the writable microprogram memory, and have our own, so to say, custom tailored machine, right? If we know the control points and accordingly write our microprogram, load into the microprogram memory, we can have users microprogrammability. Now the thing is that in such situation, that writable microprogrammable memory tends to turn the machine to be a bit slower because writable memories are generally a bit slower. Okay, but this is a very important feature. Sometimes, if you have to have your uh, machines custom tailored, okay, but generally the computers are not custom tailors. You can have your some control units, okay, which is control units of instruments, which can be user microprogrammed, okay, and that can be very useful and helpful also. Now let's come to the disadvantage of it, because it is slower than the hardware unit of comparable technology, because you can see that every time that micro instructions have to be fetched from the memory and executed, that goes through, after all, a memory cycle. Though the microprogram memory is very fast, but still it is time consuming, and therefore it is slower than the hardware unit of comparable technology. Now here you see, as I said earlier, if you have the I should say simpler addressing modes and simpler uh, instruction set, then you can have a simpler hardware, and in that case you can go for a hardware control. Otherwise, if it is complex, okay, one tends to go to a microprogram control unit. Now all these things, for example, that hardware control to have a simpler machine, simpler decoding, okay, that more number of general purpose registers, right? These are the features that RISC aims at, okay? By RISC, I mean that reduced instruction set computer aims at, right? Lastly, let us see, apart from the realizing the control units of a microprogram, through microprogram, what can be the other applications of such a microprogrammed control unit? That for intelligent instrumentation, as I was referring to a little bit earlier, for that microprogram control unit is used, okay, and you can see that if you have the hardware known, if you have the control points known, according to your own choice, according to your own need, you can implement your own control to have your intelligent instrumentation, right? Then for the case of an emulation, you can use that control unit. By emulation, I mean that, so for example, if you have a computer and if you want that this computer should simulate the behavior of another computer, you can write a microprogram, okay, that will simulate the behavior of another computer. This we call emulation. For high-level language support also this is used, as well as for operation system support it is used, okay. That's all so far as that microprogram control unit is concerned, and that is also far as control unit design is concerned. Thank you.